Welcome back to Physics 191. I'm Gerard Blanchard. Last time, we introduced the concept of rotational inertia, the capital I that appears in our rotational version of Newton's second law. In other words, angular acceleration is equal to total torque on an object divided by rotational inertia, or alpha, angular acceleration, equals tau total, total torque, divided by I, rotational inertia. So in order to use Newton's second law for rotation, we have to know how to figure out the rotational inertia of an object. Last time I told you that for a point object, for a single point of mass, going around and rotating around an axis, the rotational inertia of that point of mass is the mass of the object times the distance that it is from the axis, or I, rotational inertia, equals m mass times r squared, or the distance that the point is from the axis of rotation squared. Now normally we don't deal with a single point of mass going around an axis. Usually we're dealing with a wheel or a disc or a rod swinging around an axis of rotation, and for that we have a table that you can find in your textbook. Take a look at it here. We'll start off with a thin, hollow, cylindrical shell or a hoop. In other words, we have an object whose mass is all at the distance r from the axis of rotation, where r is the radius of the hoop or the radius of the cylinder, and the hoop or cylinder are rotating around the axis, going through the middle of the cylinder, or around the symmetry axis, going through the long way through the cylinder, or perpendicular to the hoop through the middle of the hoop. These two are the same because they share the property that all of the mass is at a distance r from the axis of rotation, so the rotational inertia of a thin, hollow, cylindrical shell or of a hoop is the mass of the cylindrical shell or the mass of the hoop times the radius of the hoop squared or the radius of the cylinder squared. So for a thin, hollow, cylindrical shell, think of a soup can for which you've cut off both the top and the bottom lids. So you've cut off both lids of a soup can and you're left with a cylindrical shell. And you're rotating it around the long axis of the cylinder. In that case, all of the mass is at the same distance, r, the radius of the cylinder from the rotation axis, or a hoop, a hula hoop, or a bracelet, in which case, and you're rotating it around an axis perpendicular to the hoop, then in that case all of the mass is at the same distance r from the axis of rotation. So in both of these cases, our equation that we saw before still holds. So the rotational inertia of this thin, hollow cylindrical shell or of this hoop is equal to the mass of the cylinder or the hoop times the radius squared. So in this case, rotational inertia is mass times r squared. Now, let's consider a solid cylinder or a solid disk. For a solid disk, think of a coin or a CD, a compact disc. Well, actually, a CD is probably not the best example because it does have a hole cut out of the middle. But if we imagined it to be, if we would imagine the hole away, so if we imagine that there were no hole in the center, then that would be appropriate. And a solid cylinder is a solid cylinder of some matter. Like if we imagine a dowel, a rod that we're rotating along the long axis of the rod, or a perfectly cylindrical log that we're rolling or spinning around the long axis of the log, then in this case, not all of the mass is at the same distance from the rotation axis. Some of the mass is closer. And so since that mass that's closer to the axis has a smaller r, then the rotational inertia of this solid cylinder or solid disk is not going to be mr squared. In fact, it's equal to 1/2 of the total mass of the disk or cylinder times the radius of the disk or cylinder squared. So in other words, a solid cylinder or a solid disk has a rotational inertia that is less than mr squared, because not all of the mass is at the extreme edge of the disk or of the cylinder. So for a solid cylinder or a solid disk, you can look on your table and you can see that the rotational inertia of a solid disk or a solid cylinder would be equal to 1/2 mr squared. Next in our table we have actually the compact disk situation, where we have a cylindrical shell or a cylindrical disk with a hole cut out of it, and then you can see that there's an equation for that. I won't get into that. There's the rotational inertia of a rectangular plate being rotated about an axis through its center. We're not going to use that in here that I can imagine, but if you had to, you could come back and find the equation that told you the rotational inertia of that plate. You'll notice that in all of these cases, the rotational inertia is equal to the mass of the object times some length squared. So we still have this idea of rotational inertia being equal to mass times length squared, just sometimes we're going to divide by, or we're going to multiply by a fraction in order to find the rotational inertia, unless all of the mass is at the same distance from the center of rotation, from the axis of rotation. Now, one that we will use, one object that we will work with in here, or you may work with in lab, is a solid sphere. You can think of a marble or a ball bearing or a pinball. That would be a solid sphere. The rotational inertia of a solid sphere is 2/5 of its mass times r squared. A hollow sphere, you can imagine what a hollow sphere is, has a rotational inertia that's a little bit higher. It's 2/3 of its mass times r squared. A rod swung around one end has a rotational inertia of 1/3 of its mass times its length squared. So that, for an example of that, you can think about a baseball bat. If a baseball bat were a uniform rod, a baseball bat's not really a uniform rod. It's a little bit heavier on one end, so you would that would change things a little bit. But as a first approximation, if we imagine that a baseball bat were a uniform rod, then its rotational inertia would be 1/3 of its mass times its length squared. So once again, a mass times a distance squared. Now a rod spun about its center, so if you think of a baton being twirled, then that has less rotational inertia. That would be 1/12 mass times length squared. Now, I don't expect you to memorize all of these, And if you're taking this class for credit and you're going to have to take a test, you will have access to this table. And when you're working your exercises, you will have access to this table, but you do have to know to refer to this table when you need to. So a table like this, or a table later on, if you don't have your physics textbook, you can find tables like this on the web in many, many, many places. There are tables like this all over the web. You can find them in different books as well. So this is something that you would refer to later on, a table similar to this. So, the rotational inertia of an object is equal to the object's mass times its some dimension, some length or radius squared, times perhaps a multiplier. And that multiplier is what you will get from a table like this. Okay, we always learn best by doing, so let's do an exercise that puts this to work for you. A spinning flywheel has rotational inertia I equals 400 kilograms meter squared. Its angular velocity decreases from 20 radians per second to 0 in 300 seconds due to friction. What is the frictional torque? Okay, you'll have to think back to our rotational kinematic situations. This is in fact a rotational non-equilibrium situation and a rotational kinematic situation. So please diagram this situation as you would a rotational kinematic situation. You'll need to pick a rotational kinematic equation, and then you'll also have to use your analog, your rotational analog to Newton's second law. So go ahead and give this question a try. Okay, here's our spinning flywheel. It is rotating, and then after some time it comes to rest. So we have T initial, omega initial, and theta initial. We might need to know that. T final, omega final, theta final. And we have angular acceleration. T initial we can set to 0. We can start our stopwatch anywhere we want. Omega initial, we are told, is 20 radians per second. 20 radians per second. Theta initial, we can call its initial angle to be 0 radians. T final, we are told, is 300 seconds. So we're given that information, 300 seconds. Omega final, we're told that the flywheel comes to rest. So we're told that omega final is equal to 0 radians per second. And theta final, we're not told anything about. We're also not told about our angular acceleration. So we don't know about our angular acceleration. We're told that there is a frictional torque. So if the object is rotating in this direction, in the positive or counterclockwise direction to begin with, then the frictional torque must be opposing that. So this is omega, that's our angular rotation, omega initial. Omega initial is counterclockwise or positive, so our frictional torque must be clockwise or negative. It's opposing the motion. So we should expect to get a frictional torque that is negative. because it is opposing the motion. Well, we can write down our Newton's second law for rotation. So rotational non-equilibrium gives us angular acceleration is equal to torque total over rotational inertia. Angular acceleration, we don't know. I'll leave that as alpha. Torque total, we have no positive torques to consider, no counterclockwise torques to consider. The only torque that we have to consider as this flywheel is slowing down is the frictional torque that is counterclockwise. So I will write minus tau F. So we're assuming that the frictional torque is in the negative direction, divided by the rotational inertia. And we were told, so I should write it up here, rotational inertia is equal to 400 kilogram meters squared. So torque frictional over 400. So we have an equation with two unknowns in it. We have to get another equation. This is a situation that we faced before with our regular kinematic situations. So from experience, we know that we need a rotational kinematics equation. And specifically, we want to find angular acceleration. So we want to find angular acceleration from our rotational kinematic equations, but we don't know theta final. So we want our rotational kinematic equation that does not include theta final. And that would be angular acceleration is equal to omega final minus omega initial over t, or time final minus time initial. And that's angular acceleration is equal to 0 minus 20. Omega final is 0, omega initial is 20. Divided by time final, which is 300, minus time initial, which is 0. And that tells us that angular acceleration is equal to 20 divided by 300. 20 divided by 300 gives us negative, because we have negative 20 actually, negative 0.0667 radians per second squared. Okay, that we can put over here into our equation, our Newton's second law equation, or negative 0.0667 is equal to minus torque frictional over 400. So we can multiply both sides by negative 1. That'll give us positive, and we can multiply both sides by 400 to bring that to the other side up here. And that would give us 400 times 0.0667 is equal to our frictional torque, or to the magnitude of our frictional torque. And so that would be 400 times 0.0667 is equal to 26.7, is equal to the magnitude of our frictional torque. And 26.7 watts, well, remember that torque is measured in Newton meters in the metric system. Our basic metric units of torque are Newton meters, or a force times the distance. And that answers the question that we were asked. Let's work another example. Two children standing on opposite sides of a merry-go-round are trying to rotate it. They each push in opposite directions with forces of magnitude 10 newtons. If the merry-go-round has a mass of 180 kilograms and a radius of 2 meters, what is the angular acceleration of the merry-go-round? And then question 2 is, how fast is the merry-go-round rotating after 4 seconds? This is actually 2 questions that we can answer at once. So please diagram the situation as a rotational kinematic situation and also a rotational non-equilibrium situation. All right, here's the merry-go-round. It is initially at rest, so we have T initial equals 0, omega initial equals 0, theta initial equals 0. We're free to call our initial angle and our initial time whatever we want them to be. The wheel accelerates, and then after a while it is rotating. T final, we are told, is 4 seconds. Omega final is what we are looking for. We're asked for how fast is the merry-go-round rotating after 4 seconds. Theta final, we don't know, but we also don't need to know. But I just wrote it down there anyway for consistency. We're told that the children are pushing on it in opposite directions with forces of 10 newtons. Here's the center, and here's the line that each of these forces makes with the direction to the pivot point of the merry-go-round. So we know that these forces are at right angles. So we know that when we calculate torques, we're going to have the sine of 90 degrees. We're told that the radius of the merry-go-round, R, is equal to 2 meters. 2 meters, and the mass of the merry-go-round is equal to 180 kilograms. Okay, that is everything. This is a 10 Newton force as well. And we have gotten everything that we can so far out of the statement of the question. And we know that this is a rotational kinematic situation, so we can write rotational kinematic. We can have, we'll have to figure out what equation to use. Well, we know that we're looking for omega final, and we don't know theta final, and we don't need to know theta final. So we're going to use our rotational kinematic equation that doesn't include theta final, and that is angular acceleration is equal to omega final minus omega initial over T final minus T initial, or angular acceleration, which we don't know, is equal to omega final, which we're looking for, minus omega initial, which is 0, divided by T final, which is 4, minus T initial, which is 0. So we're once again in the situation where we have one equation with two unknowns in it, omega final and angular acceleration, but we know that for angular acceleration we can always at least try to use our Newton's second law for rotation. So we also have a rotational non-equilibrium situation where we can write angular acceleration is equal to total torque divided by rotational inertia. which tips us off that we're going to have to figure out rotational inertia. Let's go ahead and figure that out. Rotational inertia is equal to, well, what do we have? A merry-go-round would be a solid disk, so we have to look on our table of rotational inertia, and we see that for a solid disk, the rotational inertia is equal to 1/2 mass times the radius squared. Rotational inertia is 1/2 of 180 times 2 squared, or the rotational inertia 1/2 of 2 squared is 1/2 of 4, which is 2, and 2 times 180 is 360. So we know that the rotational inertia is 360 kilograms meter squared. So we know rotational inertia. So we have angular acceleration is equal to the total torque on the merry-go-round. Well, let's look. We have one force right here that would cause the merry-go-round to rotate in the counterclockwise or positive direction. And we have another force here that would cause the merry-go-round to rotate in the positive or counterclockwise direction. So both of these are positive torques, so we can add the torques together. Torque is equal to force, which is 10 newtons, times the distance that force is from the pivot point. That distance is 2 meters, times the sine of the angle that the force makes with the line to the pivot point, which is 90 degrees. So we have sine of 90 degrees, which is 1, so I won't write that. And then we have the same thing for this force. We have a force of 10 newtons, and it's also in the positive or counterclockwise direction. So we would have plus 10 times 2 meters times the sine of the angle between the force and the line to the pivot point, which would be 90 degrees. So we'd once again have the sine of 90 degrees, which is 1, so I won't write that, divided by I, our rotational inertia, which is 360. So angular acceleration is 10 times 2 plus 10 times 2 divided by 360. And what is that? That is 10 times 2 plus 10 times 2 divided by 360. That is, angular acceleration is 0.111 radians per second squared. So we have our angular acceleration. We have our angular acceleration from our rotational non-equilibrium equation. And that answers the first question that we were asked. What is the angular acceleration? It's 0.111 meters per second squared. And now we can take that, bring it over here, and solve for the angular velocity at 4 seconds. So 0.111 is equal to omega final divided by 4, or 0.444 is equal to omega final. And we're dealing with angular velocity, so that must be radians per second. So the angular velocity, or the rotational velocity of the merry-go-round after 4 seconds is 0.444 radians per second. And that answers the other question that we were asked. Let's try another example. A chain pulls tangentially on a 40.6 kilogram uniform cylindrical gear with a tension of 72.5 newtons. The chain is attached along the outside radius of the gear at 0.65 meters from the axis of rotation. Starting from rest, the gear takes 1.70 seconds to reach its rotational speed of 1.35 revolutions per second. What is the total frictional torque opposing the rotation of the gear? Okay, this is something where you'll have to visualize the situation, diagram it. It's a rotational non-equilibrium situation and a rotational kinematic situation. We'll deal with it similarly to what we've dealt with before, and also realize that there is a frictional torque involved as well. So you have to visualize that frictional torque in the situation as well when you're drawing your diagram. So go ahead and draw your diagram, list your knowns and unknowns that you're given, list your equations for modeling this situation. Here is our gear, and here's a chain pulling on it, and we're told that it has a tension, and it's tangential to the gear, and it has a tension of 72.5 newtons. The gear starts from rest, so let's go ahead and write all that out. Time initial, we'll call that 0. Omega initial, we're told, is 0. And theta initial, we'll call 0. And we have some angular acceleration, which we don't know yet. And finally, the wheel is rotating. We have omega. There's some omega at the end. And T final. T final, we are told, is 1.7 seconds. Omega final, we are told, is 1.35 revolutions per second, which we will have to convert into radians per second, with 2 pi radians being equal to 1 revolution. That becomes 1.35 times 2 times pi, or 8.48 radians per second. And theta final, we don't know. And we also don't need to know. We're not asked for that. And we have to draw in our frictional torque. The chain I've diagrammed in such a way that the chain is causing a counterclockwise or positive torque, so the frictional torque must be counterclockwise. So it's counterclockwise with magnitude tau f. So a negative frictional torque has magnitude tau f and a direction of clockwise or negative. Well, we know that this is a rotational kinematic situation, since we have a change in time and a change in angular velocity. And since we're asked for the frictional torque, we know that this is also going to be, we're also going to need to know our Newton's second law for rotation, or we're going to need to use our Newton's second law for rotation. So we have a rotational non-equilibrium situation. And so that we know will be angular acceleration is equal to torque total divided by rotational inertia. And that brings to mind some things that we did not put in up above, and that is that the radius of the gear, radius is equal to 0.65 meters, and the mass of the gear is equal to 40.6 kilograms. There we go. So that was also given to us, and I think now we have gotten all the information that we can out of the statement of the exercise. We also need a rotational kinematic equation. We don't know theta final, don't need to know theta final, but we do need angular acceleration, so we will use our equation without theta in it. So it would be angular acceleration is equal to omega final minus omega initial over time final minus time initial. Our angular acceleration is equal to 8.48 minus 0 divided by 1.7 minus 0, and we can calculate our angular acceleration. 8.48 divided by 1.7, and that is 4.99 radians per second squared. So we have our angular acceleration, 4.99 radians per second squared. Now let's see what we can do with our rotational non-equilibrium equation. Well, angular acceleration is 4.99. Torque total. We have two torques. We have the chain, which I've set up to give us a positive torque of force of 72.5 times the distance that is from the center of the gear, which is the radius of the gear, times 0.65, times the angle that the force makes with the line to the pivot point, which is a right angle, so that'd be sine of 90 degrees, which is 1, and I won't write that, minus our frictional torque. Frictional torque is in the clockwise or negative direction, minus tau frictional. And that's what we're actually looking for, tau frictional. And then we divide by rotational inertia. Once again, this gear is a solid disk, so the rotational inertia would be, according to our table, 1/2 mr squared. Our rotational inertia is 1/2 the mass of 40.6 times the radius of 0.65 squared, which gives us a rotational inertia of 1/2 times 40.6 times 0.65 squared of 8.58 kilograms meters squared. So 8.58. And we have an equation here where the only thing in it is the frictional torque. We solve for frictional torque. We'll multiply both sides by 8.58. 8.58 times 4.99 is equal to 72.5 times 0.65 minus the frictional torque. And I can add frictional torque to both sides, which will bring it over here, and subtract this term right here, which will bring it to the other side. And that will give me frictional torque is equal to 72.5 times 0.65 minus 8.58 times 4.99, which tells us that the frictional torque is equal to 72.5 times 0.65 minus 8.58 times 4.99, which gives us a frictional torque of 4.31 Newton meters. So the question that we were asked is, what is the frictional torque? The frictional torque is 4.31 Newton meters, and as we've diagrammed it, clockwise. It is clockwise, not counterclockwise. So in the clockwise or negative direction. Remember, clockwise is negative. Let's work another example. A grinding wheel with a mass of 20 kilograms and a radius of 22.4 centimeters is a uniform cylindrical disc. When the grinding wheel's motor is turned off, friction causes the wheel to slow from 1200 RPM to rest in 60 seconds. What torque must the motor provide to accelerate the wheel from rest to 1200 RPM in 4 seconds? Assume that the frictional torque is the same regardless of whether the motor is on or off. So what we have here is we have a 3 time point situation. We start off with the wheel rotating at 1200 RPM, and then it slows to a stop, from which we can calculate the frictional torque. But then it's accelerated back up to 1200 RPM, and we can calculate the torque that the motor must provide in opposition to the frictional torque to cause that acceleration. So please diagram the situation and see if you can answer the question. Okay, here's our grinding wheel. Initially, we'll say that it's rotating like that initially. So we have T initial, omega initial, and I'm not going to write theta initial because we're not dealing with theta. We're not asked for the number of revolutions or the angle. So I'm just not going to write theta. We know that it's not needed. And we'll set T initial equal to 0. Omega initial is 1200 revolutions per minute, which we will have to turn into radians per second, with 2 pi radians per 1 revolution and 1 minute per 60 seconds equals 1200 times 2 times pi divided by 60 is 126 radians per second. The wheel comes to a stop. It has an angular acceleration. The wheel comes to a stop at T final of 60 seconds. We're told that it comes to rest in 60 seconds. And so omega final is equal to 0. And then it starts again with a different alpha. And then finally, we have a new T final and a new omega final. Our new T final is 4 more seconds. So it goes from rest to rotating again in 4 seconds. So that must be 64 seconds. And omega final is 1200 revolutions per minute, which we've calculated is 126 radians per second. And we are told that the mass is equal to 20 kilograms, and the radius is equal to 22.4 or 0.224 meters. And so the rotational inertia will be 1/2 mr squared, or 1/2 of 20 times 0.224 squared, which is 1/2 of 20 times 0.224 squared, which is 0.502 kilogram meters squared. So we have diagrammed our situation. The wheel is initially rotating. It comes to rest in 60 seconds, and then it comes back to its operating speed in 64 seconds. So we have 2 times here, so we'll have to be careful to keep our times separate. I'll draw a line down the middle of the page so that we can keep our times separate. And in this stage, we just have frictional torque opposing the motion. And in this one, we have the torque of the motor and frictional torque opposing that. Okay, our first task is to calculate the angular acceleration of the wheel from here to here. So that is a rotational kinematic question, which we will write with angular acceleration is equal to omega final minus omega initial over t final minus t initial. Our angular acceleration is equal to 0 minus 126 divided by 60 minus 0, which tells us that our angular acceleration is negative 126 divided by 60, or 2.1. Negative 2.1 radians per second squared. So we know that in the first half of the question, our angular acceleration is negative 2.1 radians per second squared. Now that we know the angular acceleration, we can calculate the frictional torque using our rotational Newton's second law. So we have rotational non-equilibrium, and that tells us that the angular acceleration is equal to the total torque divided by the rotational inertia. As the wheel is slowing down, the only torque is the frictional torque. So we have an angular acceleration of negative 2.1 equals minus the frictional torque divided by the rotational inertia of 0.502, and that tells us that the frictional torque, we have 2 negatives, so I'm going to multiply both by negative 1 and multiply both sides by 0.502. That says that 2.1 times 0.502 is equal to our frictional torque. And what does that equal? 2.1 times 0.502 is equal to 1.05, and that would be Newton meters is the magnitude of our frictional torque in this situation. So that gives us our frictional torque. Now we have to go to the second half of the question. Torque friction is 1.05. The second half of the question is when the wheel is accelerating again, what is the torque of the motor that's causing it to accelerate? Well, we do the same thing over again. Rotational kinematics we'll use to calculate our angular acceleration. Alpha is equal to omega final minus omega initial over T final minus T initial, where our T final from before is now our new T initial, and our omega final from before is our new omega initial. So the angular acceleration is equal to omega final of 126 minus omega initial of 0 divided by T final of 64 minus T initial of 60 tells us that our angular acceleration is 126 over 4. 126 divided by 4. Our angular acceleration is now positive 31.5 radians per second squared. So that is our angular acceleration for the second time period over here, 31.5 radians per second squared. And now we can use our rotational non-equilibrium to calculate our torque. Our angular acceleration is equal to torque total divided by rotational inertia. Angular acceleration is 31.5. That is equal to our torque total. Our positive torque is the torque of the motor minus the frictional torque of 1.05 divided by the rotational inertia of 0.502 gives us an equation that we can solve for the torque of the motor. We multiply both sides by 0.502, 31.5 times 0.502 is equal to torque of the motor minus 1.05, and we can add 1.05 to both sides. 31.5 times 0.502 plus 1.05 is equal to the torque of the motor. And that comes down to 31.5 times 0.502 plus 1.05. That is 16.9 Newton meters is the torque of the motor. And that was a question that we were asked. So we solve our rotational non-equilibrium situations in a very similar way to the way that we solve our non-equilibrium kinematic situations. Just now we're using, instead of our linear equations, we're using our rotational equations. So that's it for now. Until next time, think physics.